Hi everyone. Today is April 1st and we're going to talk about exponential and logarithm modeling, okay? We're just going to jump right into some examples, all right? So here's the first example. World population in billions during year X can be modeled by P of X. So P of X represents the population where X represents the year, and the population is going to give us, it's going to give it to us in billions, all right? So if we get a number like 3, that if P of X is 3, that actually means 3 billion, okay? If we get P of X is equal to 7, that would mean 7 billion, okay? So here's the first question. What was the world population in 1994? Include units in your answer, okay? So our X is our year, so we're going to put that in. So really what we're going to find here for this problem is we are trying to find P, the population, in 1994. Okay, so that's what we're trying to find here. So we would just write P of 1994 would equal 3 times 1.017 raised to the 1994 minus 1960, okay? And so we're going to need to do the subtraction, okay? So this would be equal to 3 times 1.017 raised to the 34th power, because 1994 minus 1960 is 34, okay? So we're going to put this into our calculator. I'm going to go to my calculator. We're going to put that in, all right, and see what it comes out to be. So in our calculator, we're going to put in 3 and then parenthesis and then 1.017 and then close the parenthesis and then raise that to the 34th power. And that gives us 5.321 because we'll round to 3 decimal places. Okay, and we'll go back and we'll put that on our paper. All right, so on our paper, we're going to put this is approximately 5.321. Okay, so what that means is 5.321 billion people. So I want you to write a sentence with this, okay? So this happened in 1994. In 1994, the world population was 5.321 billion. Okay, let's go to part B. All right, for part B, when will the world population reach 7 billion? And then interpret your results, okay? So what we're trying to find now is the year that this happened. So that would be P of X is equal to 7, right? And we need to solve this. So we need to solve P of X is equal to 7. So that would be 3 times 1.017 raised to the X minus 1960 is equal to 7, because this is our P of X. Okay, so we're just taking the P of X out and replacing it with what it's equivalent to. Okay, so to go through and do this, we need to solve this for X. But to solve this for X, I got to get the base first. Okay, I got to get rid of this 3. Okay, so I'm going to divide both sides by 3. So this would give us 1.017 raised to the X minus 1960 is equal to, and this side would be 7 over 3, 7/3. Okay. All right, so how do we get the variable down out of this exponent? Well, we're going to take the logarithm, okay? And in this case, I'm going to take the natural log. You can actually use any logarithm, but I'm going to use ln, okay? So we're going to take the natural log of both sides. So the natural log of 1.017 raised to the x minus 1960 is equal to the natural log of 7/3. Okay, so now what I'm going to do is I can use the logarithm properties that if you have the logarithm of a base to a power, that's the same as the power times the logarithm of the base. Okay, so I'm going to bring this down in front. Now, this is a difference, so I have to put parentheses around it. Okay, so it's going to be x minus 1960 times the natural log of 1.017 is equal to, and then on this side, I'm going to use logarithm property too, because the natural log of 7/3 can be rewritten as the natural log of 7 minus the natural log of 3. So I'm going to do that too. So the natural log of 7 minus the natural log of 3. And that's a logarithm property, okay? I'm going to write these out. So to go from here to here, we used the natural log of x raised to the r is equal to r natural log of x. And then from here to here, what we did is we took the natural log of x over y is equal to the natural log of x minus the natural log of y. And those are some logarithm properties that I used, okay? All right, so now we got to get to this x, right? But to get to this x, I'm going to have to multiply the natural log of 1.017 times the x. I'm going to need, this is actually a number. Like I could put that into my calculator and I would get a number. So what I need to do is distribute that, okay, with the x and the 1960. So this becomes x times natural log of 1.017 minus 1960, the natural log of 1.017, is equal to the natural log of 7 minus the natural log of 3. Okay, the only term that has an x involved in it is this one. So I need to get this by itself. So I'm going to add 1960 natural log of 1.017 to both sides, which would result in giving me x natural log of 1.017 is equal to the natural log of 7 minus the natural log of 3 plus 1960 natural log of 1.017. Okay, so now how do I get this x by itself? Well, what am I doing to the x? I'm multiplying it by natural log of 1.017. So what I want to do is to undo the multiplication, I'm going to divide. Whatever you do to one side, do to the other side. So I'm going to divide both sides by natural log of 1.017. And that would give me x is equal to the natural log of 7 minus the natural log of 3 plus 1960, the natural log of 1.017, all over, big long fraction bar, right? Okay, all over the natural log of, excuse me, natural log of 1.017. Okay, so we're going to go back to our calculator and we're going to put this into our calculator to figure out what the heck number is this, right? Like I can't tell what number it is by the way we wrote it, okay? So by putting it in the calculator, we'll have a better understanding because this x is the year in which this should have happened, okay? All right, so let's go back to our calculator and we'll do that. All right, so what we want to do next is in our graphing calculator, or you could be using Desmos too, okay? Alpha, fraction bar, right? And then we want to get natural log of 7, so that'd be ln of 7, close the parenthesis to end the that natural log, and then minus, and then natural log of 3, and then plus 1960 or 1960 ln of 1.017, close the parenthesis, and then over natural log 1.017, okay? And then press enter and we'll have our answer, okay? So this should have happened in 2010. The population should have reached 7 billion, okay? All right, so X, we're gonna go back to our paper and put this in, okay? So it's the 0.263, 0.263 or 0.264, okay? That's how many months, because this is the year and this is months. So even if we go like 2010 and 2 months, that's still the year 2010, okay? All right, so we're gonna just say what year this happens in, okay? All right. So on our paper, we're writing X is about approximately 210, all right, 210. Let me erase that, 2010. 2010.264. Okay, and then this interpret the results. Okay, so what does this mean? This means, I'm gonna slide it up just a little bit. Okay, this means in 2010, the world population will reach 7 billion. Okay, or the world population will reach 7 billion in 2010. And all of this stuff is real data. I got this from a book a few years ago, but it's all this. If you look it up, the world population, it was right around 2010 when it reached 7 billion. You can look it up on Google and see and ask Siri when this happened. Okay, and it can tell you, and it's probably pretty close to 2010. Okay. All right, so now let's go to the next example. Okay, so example 2. All right, so turn the page. So for example 2, this one is in developing countries, there's a relationship between the amount of land a person owns and the average daily calories consumed, okay? So if you own land, you're probably gonna eat more, right? Okay, and that's basically what this says. And the relationship is modeled by the formula C of x is equal to 280 natural log of x plus 1 plus 1,925, where X is the amount of land owned in acres and 0 is less than or equal to X, which is less than or equal to 4. So this works. Okay, so basically this is the domain for this function, right? And it's between 0 and 4, including 0 and including 4. So this works for somebody who owns between 0 and 4 acres of land, okay? So X, what we put in is the number of acres. What we get out is the average daily calories that the person consumes, okay? So for this first part, okay, find the average caloric intake for a person who owns no land. So you don't own any land, right? So that would be, we want to find, in this case, C of 0, because X represents the amount of land and we don't own any land, right? So if we want to find C of 0, that'd be C of 0 is equal to 280, the natural log of 0 plus 1 plus 1925, okay? So this is equivalent to 280, the natural log of 1 plus 1925. Okay, now this is one we can do without a calculator. We can actually find the natural log of 1. Okay, why? Because the natural log of 1 is equal to the natural log of, and we want to be able to rewrite 1 as e to a power, and we can, because e to the 0 power is 1, right? E to the 0 and 1 are the same thing. Okay, but now we can read this one and tell, oh, this is just going to be 0, right? So this becomes 280 times the natural log of 1, which we just showed over here is 0. So times 0 plus 1925. Well, 280 times 0 is 0, right? So it's 1925. Okay, so what does this mean? Okay, I'm going to slide it up just a little bit. Okay, so what this means, a person who owns no land has an average daily calorie, the number of calories consumed daily on average is 1,925. Okay, all right, so let's write that down. Okay, so a person who owns no land has an average daily caloric intake of 1,925 calories. Caloric intake is just how many calories you take in. Okay. All right. And that's how you answer the first one. Okay. Let's go to part B. So for part B, we want to determine symbolically the number of acres owned by someone whose average intake is 2,000 calories per day. All right. So if you only are taking in 2,000 calories per day, how much land do you own, right? So that means we want to solve this equation. C of X is equal to 2,000, right? So from the function above, we know that this C of X is the 280 natural log of the quantity X plus 1 plus 1925, right? So we're going to put that in for C of X. So we know that 280, the natural log of X plus 1 plus 1925. And we know that's equal to 2,000, right? Because we were trying to solve this for this X right here. But to get to this x, I need to get x plus 1. But before I get to x plus 1, I got to get to the natural log. But before I get to the natural log, I got to get to the 280. I need to get rid of this plus 1925 first. So to do that, the simplest way is just to subtract 1925 from both sides. So that would result in 280. The natural log of x plus 1 is equal to, and then 2000 minus 1925 is just 75. Okay. All right. So now I need to get to the natural log part, right? So I need to divide both sides because I'm multiplying by 280. So this becomes the natural log of x plus 1 is equal to 75 divided by 280. Now, 75 divided by 280 actually reduces, right? Because they're both divisible by 5. Okay. All right. So this becomes the natural log of x plus 1 is equal to, and this reduces to 15 over 56, okay? And you can use a calculator to reduce this, all right? I'm just divided both of those by 5, okay? Now, we need to get rid of the natural log to get to the x plus 1 part, right? So how do we undo natural log? Well, we need to exponentiate to get rid of any logarithm, right? So what base are we going to use to exponentiate with? Well, this is natural log, which means it's base e. So we're going to exponentiate with base e. So this becomes e to the natural log of x plus 1 is equal to e to the 15 over 56 power, right? And e raised to the natural log, those undo each other. So you're going to be left with x plus 1 is equal to e to the 15 over 56. And then we're going to subtract 1 from both sides. And that would result in x being equivalent to e to the 15 over 56 minus 1. Okay, so now we're going to need to go and we're going to need to put this into our calculator because this doesn't really give me an understanding of like how many acres is that, right? So to get the decimal approximation of this number is helpful to understand like how much is that, okay? So we'll put this in our calculator. So from our graphing calculator, we're going to go and we're going to type in e raised to the, okay, and this is a fraction. So there's a couple ways. You could do the division key, or I'm going to do the fraction bar, okay? E raised to the 15 over 56. And then, okay, right now I'm up in the exponent, so I would need to come down. So I'm going to do my right arrow and then I'll come down because it needs to be on the same level as the e right here, okay? So minus 1, and then press enter and we'll have our answer. So 0.307, okay? So that's 0.307 acres. That's how many acres they would own, okay? All right, so let's go back and we'll write this on our paper. All right, so from our calculator, we got, and I'm gonna come up here because I'm running a little bit of room. So X is about 0.307, and that's acres. All right, so that's how much land they would own, okay? So we could write this out, okay, to state this, right? Someone, we could just say someone whose, and we can almost just restate the question, right? Someone whose average intake is 2,000 calories per day owns 0.307 acres of land. Okay. All right. So there's a definite correlation between how much land you own and how much you eat. Okay. In these developing countries. Okay. All right. So turn the page and we'll do example 3 next. In example 3, it says the gap between organs available for transplant and people who need them has widened. So in 1999, about 60,000 people were waiting for organ transplants. And in 2007, this number had increased to 100,000. Okay. So this trend can be modeled by this exponential function here. Okay. Where C and A are constants. Okay. So I want to approximate C and A if the unit for T is thousands of people. Okay. So we know this T of X is going to be the year, okay? And T of X is the number of people, but it's going to be thousands of people. So again, if we have like 5, that doesn't mean 5 people. That means 5,000 people, okay? So what we know from here is that in the year 1999, there were 60,000. So that would mean for this function that T of 1999 is equal to 60,000 people. Okay. And then we also know that in 2007, it was 100,000. So that would be T of 2007 is equal to 100,000. Okay. So putting 1999 in here, okay, into the function for X, we know we're going to get out 60,000 people. Okay. So that'd be 60,000 is equal to C times A raised to the 1999 minus 1999, right? So that's going to be 0. So that's going to be 60,000 is equal to C times A to the 0 power. But remember, A is a number, right? It's a positive number. And it can't be 1, but it can be between 0 and 1. It can be bigger than 1, right? But it has to be positive, right? And so that means if we raise it to the 0 power, this becomes 1. So that's 60,000 is equal to C times 1. Well, that's just C, right? So 60,000 is equal to C. We know what C is now, okay? Now over here, we need this one to figure out what the A is, okay? So we know from this that 100,000 is equal to C times A to the 2007 minus 1999. Now, I purposely put the C here. I know what it is already, and you could have just put 60,000 here, but I wanted to show you this is going to simplify, and this is going to become 60,000. So what we now have is 100,000 is equal to C, which is 60,000, times A raised to the, and this would be 8. Okay, so now the next thing I want to do is I need to get to this A, but before I get to A, I need to get to A to the 8th power, okay? So what I'm going to do is I'm going to divide both sides by 60,000 because that's what I'm doing to A to the 8th. I'm multiplying by 60,000. So I need to divide both sides by that. Okay, so 100,000 divided by 60,000 is equal to A to the 8th power. Okay, so we're going to reduce this, right? And this becomes, all of these zeros could cancel, okay? Because they're all multiples of 10, okay? So then this becomes 10 over 6 or 5/3 is equal to A to the 8th power. Okay, so now you could do this with roots, but we want to avoid roots. The other way you could deal with this to get rid of this 8 is to raise this to the reciprocal power. Now, as long as you do that to both sides, you're good. So this becomes 5/3 raised to the 1/8 power is equal to a to the 8th raised to the 1/8 power. Now, why can we do that? Okay, if you raise it to a power, right? If we take a base raised to a power and we raise that whole thing to another power, what do you do with these exponents? Well, you multiply them. And so because we're raising it to the 1/8 power, when we go to multiply it, 8 times 1/8 becomes just 1 or a, okay? So this one is not going to be easy to do, right? So we're just going to leave it as 5/3 raised to the 1/8. You can't get a nice number out of this, okay, without putting it into your calculator. All right. So this is 5/3 raised to the 1/8 power is equal to a. That's our base. Okay. So now let's write our function. Okay. So I'm going to come back over here. All right. T of x is equal to my c, which is 60,000. Okay, and then I'm multiplying that by a, right? And a is this 5/3 raised to the 1/8. So I'm gonna have to use a bracket here. Okay, so it's 5/3 to the 1/8, and I'm using brackets to put around my a. Okay, and then I'm gonna raise, this is my a, and I'm gonna raise that to the x minus 1999 power. We are gonna write this simpler. Okay, all right. So now, what is T of x? Well, T of x is equal to the 60,000 times 5/3 to the 1/8, raise that to the x minus 1999. Well, what do I do with these? Well, I multiply these, right? And 1/8 times x minus 1999 is just x minus 1999 over 8. Okay, so that would be our function, okay? So T of x would be equivalent to 60,000. Okay, because we're doing math, you don't want to round this and use a rounded value. Why? Because this is the exact value from the data that we're getting, okay? So you don't want to put a decimal in here. That would be incorrect, okay? We want to be specific with our math, okay? So then this would be 5/3 raised to the, and this would be x minus 1999 over 8. Okay, and that will give us, if we put it in the year, that will give me how many thousands of people are waiting for these organ transplants. Okay, all right, so let's go to part B now. Okay, actually I'm going to box this. This is the function that we're going to use for part B. Okay, we're going to use T of x, the function we just came up with, to estimate the number of people who were waiting for organ transplants in 2004. Okay, so that would be the x, right? So we're going to do T of 2004. That's what we need to find. Okay, I should write find. That's what we're trying to find. Okay, so T of 2004 would equal 60,000 times 5/3 raised to the 2004 minus 1999 over 8 power. Okay, so then that would be 60,000 times 5/3 raised to the, okay, and then 2004 minus 1999, that'd be 5. So this is going to be raised to the 5/8 power. Okay, so now we're going to go and we're going to put this into our calculator and we're going to get an estimate for how many people were waiting. All right, so let's go to our calculators now. So in our calculator, we're going to type in 60,000 and then parenthesis and then our fraction bar. And it was 5/3. And then come out of the fraction and close your parenthesis. And then raise that to the 5/8 power. So we can do another fraction bar. You could also do 5 divided by 8 up in the exponent, okay? So 5 over 8. And we can press enter. and we'll get it. So this means 82,567.041, right? Rounding. Okay, so that means 82,567 people would be waiting for an organ transplant in 2004. So I'm going to go back to our paper and I'm going to write this answer down, okay? So from our calculator, we got 82,567.041. Now this can't, that's not really a person, right? That's just a part of a person. So we can't really count it for this, all right? So the number of people waiting for organ transplants. Let me change that to waiting. I got ahead of myself. Waiting for organ transplants in 2004 was 82,567 people. Okay, and that's it for example number 3. All right, for example 4, it's basically, this is going to be a physics problem, okay? This is called Newton's law of cooling, all right? And if a hot object is put in a room with temperature T sub O, okay? So T sub O is this room temperature. Then according to Newton's law of cooling, the temperature of the object after time t is modeled by this function. Okay, capital T is the temperature, all right? And little t is the time, okay? And where 0 is less than a is less than 1. So this a has to be a number between 0 and 1. D is the initial temperature difference between the object and the room, okay? All right, so a pot of coffee with temperature of 100 degrees Celsius, okay, is set down in a room with a temperature of 20 degrees Celsius. Okay, this T sub O, what's going to happen here? All right, if you think about just the natural part of this is this coffee is going to cool down. Well, what also is going to happen is the room temperature is going to come up because of the coffee. Now, how much it comes up isn't very much, because there's more volume of air in the room than there is volume of coffee. Okay, so here we go. Okay, so this is our T sub O right here. Okay, and then we also know the coffee cools to 60 degrees Celsius after 1 hour. Okay, so that's going to tell me my time in this is going to be in hours. Okay, all right, so from this I know it's going to cool, right? The coffee starts at 100 degrees, it's going to cool, and it's in a medium, in a body that's 20 degrees Celsius. And when I mean body, like the body of air, okay? Not like a human body, okay? All right, so this is telling me that T sub O is 20, okay? So T sub O is equal to 20. The D is the difference between the object and the room, okay? So that would mean D is equal to, and that difference would be 100 degrees minus 20 degrees, okay? So 100 degrees minus 20 degrees, and that would give you 80 degrees, okay? And then what else that I know is this, that I know that T sub 1 is equal to 60. Okay. All right. Now, our time unit is in hours. Okay. All right. And our temperature is in degrees Celsius. Okay. So we can start writing our function. We know from these two that our T, capital T, temperature as a function of time is equivalent to 20 plus 80 times A raised to the T power. Okay. Now I know if I put 1 in here, okay, I know I'm going to get 60 out. So that would mean 60 is equal to 20 plus 80 times a to the first power, okay? All right. So now what I'm going to do next is I'm going to subtract, because I got to get to this a, right? And it's really just a, right? So this is 20 plus 80a. So I'm going to subtract 20, and that would give me 40 is equal to 80a. And then 40 over 80 is a. Well, that would be 1/2, right? So that reduces to 1/2. So I know my a is 1/2. Okay, so that means t of t is equivalent to my 20 plus 80 times 1/2 raised to the t power. Okay, t is in hours. This is going to be important. Okay, t is in hours. Capital T is in degrees Celsius. Okay, so to use this function, this is going to be really important. To use this function, I have to put in hours, and I will get out degrees Celsius. Okay, or if I know the degrees Celsius, I can put that in, and I can get the time that it would take to cool to that temperature. Now, that time would be in hours. Okay, so we got to be careful on this. Okay, all right. Okay, so here we go. All right, let's go to part B. All right, so for part B we're going to use this function that we came up with in part A, okay? And we're going to find the temperature of the coffee after half an hour. Now, half an hour is 30 minutes, right? So half hour is 30 minutes. But we would be wrong if we put 30 in for T. Why? Because T is not being measured in minutes, it's being measured in hours. So how many hours is a half an hour? Well, it would be 0.5, right? Okay. So basically this question is asking you to find is T of 0.5. Okay? We want to find that. So T of 0.5 would be equal to, and it would be 20 plus 80 times 1/2 raised to the 0.5 power. Okay, so we're going to go to our calculator and we're going to put this in. So typing in 20 plus 80, and then parenthesis and fraction bar, 1/2. And then raised to the 0.5 power. Okay, and we get 76.568 or 76.569. Okay, we'll go back to our paper and we'll record this. From the calculator, what we wound up with is 76.569, and this is in degrees Celsius. Okay, so after half an hour, the temperature of the coffee is 76.569 degrees Celsius. Okay, now the next question. How long did it take for the coffee to reach 50 degrees Celsius? Okay, so that's asking for the time, right? So that means we're going to need to solve, okay, capital T of lowercase t is equal to 50 degrees Celsius, right? Okay, all right, so I'm going to slide my paper up and then we'll finish this off. Okay, from our function, we know that T of t is 20 plus 80 times 1/2 raised to the t power, and that's going to equal 50. Okay, so what I need to get to this t, right? But before I can get to the t, I need to get 1/2 raised to the t. Okay, before I can do that, I need to get to 80 times 1/2 raised to the t. So I need to get rid of this 20 first. So I'm going to subtract 20. So that gives me 80 times 1/2 raised to the t power is equal to 30. Okay, so now I need to get to this 1/2 raised to the t. So I need to get rid of this 80. I'm multiplying by 80. So I'm going to divide both sides by 80. And that would result in 1/2 raised to the t is equal to 30 over 80. Now 30 over 80, those are both divisible by 10. So that becomes 3/8. So now I have 1/2 raised to the t is equal to 3/8. Okay, now what can I do to undo this? Well, I'm going to use natural log. Okay, you can log both sides. Okay, because that logarithms will undo exponentials. Okay, so that would allow me, if I take, and it doesn't matter what type of log, but I would use either ln or log base 10 because we have buttons on our calculator that do that. Okay, so I'm going to take the natural log of both sides. Okay, so that would result, I'm going to come up here, that would result in the natural log of 1/2 raised to the t is equal to the natural log of 3/8. Okay, so we're going to use logarithm properties because if you have a logarithm of something raised to a power, that's equivalent to the power times the natural log of this base. So this becomes t natural log of 1/2 is equal to, okay, and here we're going to use another logarithm property because the natural log of 3/8 is equivalent to the natural log of 3 minus the natural log of 8. So I'm going to rewrite this as the natural log of 3 minus the natural log of 8. Okay, now to get this t by itself, I'm going to divide both sides by natural log of 1/2. So t is equal to the natural log of 3 minus the natural log of 8 over the natural log of 1/2. Okay, now this could be rewritten because the natural log of 1/2 is the natural log of 1 minus the natural log of 2. So we could actually write this out, the natural log of 3 minus the natural log of 8 over the natural log of 1 minus the natural log of 2. But what's the natural log of 1? That's one we should know. We should just know, okay, the natural log of 1 is, and what would it be? It would be 0. Okay, why though? Why? Okay, so the natural log of 1 is equal to the natural log of e to the 0, and that would mean natural log of 1 would have to equal 0. Okay, so what this means is this becomes t is equivalent to the natural log of 3 minus the natural log of 8. Now, since this is 0, it's just going to become negative natural log of 2. And we can put this in our calculator and get an approximate answer. So I'm going to go to my calculator and I'm going to put this one in. All right, so typing this in, I'm going to press alpha x to get the fraction bar, and then it's natural log of 3, and then minus the natural log of 8, and then over, and then negative. Make sure you don't use minus because that would give it create an error. Okay, so negative natural log of 2, and we get 1.415. Okay, so we'll go back to our paper and we'll record this number. So from the calculator, we get 1.415. Okay, so that's 1.415 hours. Okay, so it would take 1.415 hours for the coffee to reach 50 degrees Celsius. Okay, and that's the end of our examples for today. Okay, I'll get the assignment sheet out and we'll go over what's next. Okay. Okay, so what I want you to do is worksheet ELF 9, and that's going to be 4-1. Okay, and then I'm going to assign this. There's no video that will go along with this. I just want you to do worksheet ELF review. Okay, and I'm going to assign that on April 2nd. Okay, all right, you guys take care. Can't wait to see you. Hopefully, we'll see you soon. Okay, bye.